G'day everyone. Day 2, acoustomagnetic electronic article surveillance systems. So you've probably seen these tags on things that you've purchased in stores. They're an anti-theft device. They're used to mark a moderately or high value item that if someone attempted to shoplift out of the store, there'll be a portal that you have to walk through where a 58 kHz magnetic field is used to interrogate the tag and see if it hasn't been deactivated by a deactivator that looks something like this. It may actually be built into the checkout bench, so if you walk through the portal, an alarm will sound and someone will come and take you to the back room and have a chat to you or whatever. The tags use an interesting mechanical oscillator that's driven. It's a magnetostrictive piece of met glass. I don't know if it's actually met glass brand, but some kind of amorphous metal. For some reason, most tags seem to have 3 elements in them. It's probably a sensitivity thing, but there's also a bias magnet inside the tag. So here's a tag that I've pulled the strips out of. You can see inside the body there, still stuck to the adhesive label, is a little bar magnet, and the 3 resonator strips themselves. They're mechanically resonant at 58 kHz, and they are excited by the transmitter. So, this is a frisking wand, and inside the deactivator, as we'll see in a minute, there's a very similar circuit to what's inside the frisking wand to detect the tag in the first place so it can be deactivated. But the frisking wand basically generates these 1 to 2 millisecond long pulses about 50 times a second, and uses those to ring up the tag. So as you can hear here, the thing's emitting these little pulses of 58 kHz radiation, and they ring up the tag. In the absence of a tag, there's a Q killing circuit that actually turns off. They normally use a resonant transmitter for efficiency. So if you just turned off the transmit drive waveform, it would take a while for the transmit resonator to dump its energy by losses. So they normally have some way of shutting down the transmission pretty quickly to make sure that the space just after the transmission is available for listening by the receiver. So the receiver is there to detect where the tag is present. The rung up resonator and the magnet are then ringing down, and they re-radiate that magnetic signal that can be picked up by the same coil, or sometimes another coil, or a bucking coil. I think the reason why, I haven't taken this guy apart yet, but I think the reason why it has this spreader thing in the middle is actually because it has a bucked coil arrangement where the illuminating coil is just a normal kind of planar solenoid, and then there's a figure of 8 pickup coil. But that may or may not be right. We'll have a look at that later maybe, but not today. So here I've got a tag sitting in a coil, just a couple of turns of wire, that's connected to the oscilloscope. You can see if I put the apologies for the handheld video, by the way. I cannot find my tripod. I will attempt to find it in the next day or so because it's getting annoying. Okay, so this is an active tag. You can see on the oscilloscope what's actually happening. That's the drive waveform. And then if I couple to the tag a little bit, you can see that after the main transmit pulse, there's a ring down. So let's see if I can get a good coupling to it here. Yeah. So that ring down is what the actual system is detecting. And in the absence of that tag, or if the tag was deactivated, that would not be present. So let's have a go with the deactivator. This deactivator has a counter on the front that just shows how many tags it's killed today, or since last power cycle. So this tag, if I place it, you can hear the click, and now it won't respond to it again because the tag is deactivated. The frisking wand will no longer detect it, and that tag is, for all intents and purposes, now deactivated. But what you can do is you can reactivate it. So if I go over and have a magnet here, and I re-gauss that little bar magnet inside, it should now work again. And I can do this as many times as I like. I can go and put it on the deactivator, bang, it's dead. And you see that the deactivator can't recognize it. Neither can the wand. And I can go and re-gauss it. Polarity doesn't matter either. I can magnetize this in either direction, and now it should be degaussed again. If I got it good enough, sometimes you don't gauss it well enough. Yep, there we go. And now it's dead again. It's not being detected. Okay, so what's inside the actual deactivator? It's pretty straightforward. It has a transmit coil that's also sending out those pulses. It's pretty much exactly the same in terms of its illuminator as the wand. It's slightly shorter though. For some reason it's closer to a millisecond, whereas the handheld ones are more closer to 2 milliseconds. But the exact value isn't really. It probably has a trade-off between sensitivity and update rate. This big capacitor here is charged up to 290 volts, and that is what does the degaussing. So when a tag is detected, there's basically a switch that connects that to the coil, and it dumps the huge pulse of current through there that then rings down, and that ringing waveform is what degausses the little bar magnet and deactivates the tag, and you can reactivate it there with a little DC magnet. But the rest of it's pretty straightforward. There's a beeper that I disconnected because it beeps every time it does it really loudly, and it's super annoying, but it's a straightforward circuit. I didn't bother to reverse engineer it any farther than say, yeah, there's a H-bridge for driving it and a big switch for degaussing. But yeah, the magnet is the really interesting part of this, because if you think about it, because the met glass saturates in a pretty weak field, if you just put it in an oscillating magnetic field, it's going to generate the harmonic energy, but not the fundamental energy. But if you have this little bias magnet, then that allows the transduction of the mechanical oscillation back into magnetic radiation. But when you take away that bias, then it can no longer do that. So it's really interesting that sort of that little magnetic field that's partially biasing the strip is what enables it to actually perform this transduction between mechanical and magnetic fields. The strips themselves are they're very interesting. This is actually a good way to get small pieces of met glass rather than buying a big strip of met glass. Met glass isn't really that expensive, but if you wanted little pieces for some experiments, maybe to build a magnetometer or just to play with it, then you can buy these tags in quantity. Like you can get huge. This is just one strip out of a lot of 1,000 or something that I bought for a few bucks, so they're not very expensive. And sometimes you can actually do this situation where when you've taken the tag apart, the little resonators are damped, so they don't want to oscillate as easily, but you can still sometimes get, if you place them back together, you can still get them to trigger the wand here. Yep, but it's much less sensitive. So only one actual resonator is required. I think the fact that there are multiple is for that very reason, is for sensitivity, is but it might have also something to do with the magnetic flux density from that little bar magnet. The exact modes of vibration and the magnetic alignment and everything I haven't entirely worked out yet. I'm pretty sure it's longitudinal, but if you think about the speed of light, speed of sound in a piece of met glass and what it might be, magnetostrictively resonant at, kind of makes sense. But there's some ways we could work that out, and maybe we'll talk about that in a future video. So yeah, this one's pretty quick, straightforward video for today, and we might do some more amorphous metal, interesting magnetic properties in the near future. Alrighty, have a good one. See you tomorrow.